Okay, sorry about that. I'm recording. The old content. So for those who are watching the video on YouTube, we've done a bit of review. To this point, we're about 15 minutes into the lecture, but all we've done so far is a review of correlation, and we're reviewing now z-scores. If you go to the end of last week's lecture, you can see that content again, and then join us here, maybe the last 10 or 15 minutes of last week's lecture before you jump back into the lecture today. Again, we're talking about z-scores right now. Let's look now at what the centering operation of the z-score does and the scaling component. Again, the numerator is the centering operation. When we look here, the numerator, xi minus x bar, recenters the distribution, and the denominator, s of x division 1 over s of x rescales it, or rather xi minus x bar over s of x, rescales it to be a standard deviation unit of measurement rather than the observed unit of measurement, whatever that happens to be. In this case, it's a percentage. So here's what we got. And you know what I'm going to do? I'm going to show you something a little fancy to make the plotting easier, but you don't need to worry about that just yet. So we're going to select all three of these variables, scale, centered, and actually I don't want scale. I just want school for now. Okay, so I'm going to select all those, and we can see that I have those three measures. And then from there, what I'm going to do is I'm actually going to use a weird function called pivot wider pivot longer. That's really helpful when I want to make faceted plots in ggplot. And it's going to take what we call this data right now is a wide format, but I'm going to convert it into a long format, where effectively what I'm going to do is I'm going to take the variable names and turn those into a variable themselves. And I'm going to put each of the values for the measures in individual rows. It sounds a little funky, but you'll get it in just a second. We'll call names2 equals operation, and we'll call values2 equals score. I'll z-score. All right. And I need to specify the columns I'm using. So for a pivot wider, what I'm going to do is I'm going to reshape it. First, I'm going to tell it what columns I'm using. Calls is going to be equal to secondary school through secondary reshaped. Names are going to go to operation. Values are going to go to z-score. We'll readjust that. Okay, cool. So let's look at what this looks like now. Before, we had a 3-column data frame with secondary school, secondary centered, and secondary reshaped. And then we had 151 observations, right? What we're going to do now is we're actually going to have 3 times 151 observations, but only 2 columns, right? We're going to make all those values go into a single column, and then we're going to have a second column that labels which variable it is. So that's what we have here. For the first observation, secondary school is 25.2, secondary centered is 0.798, secondary reshaped is 1.59. Right now, this all sounds kind of funky, but let's see what the operations show us. And actually, let's include secondary scale in there, just for fun. Okay, so we can kind of see how the whole operation goes. Yeah, okay, that'll work. And then we're going to put a geom histogram on our ggplot, and we're going to do a facet wrap by operation. Okay, so this looks complicated and it's a bit tricky, but this is one way to reshape data really quickly for sophisticated data visualizations. Okay, and of course it didn't work. Secondary scale doesn't exist because I didn't select it. So let me select it. Let's try that again. All right, I need to change this to z-score now. I renamed things. Let's remove the summary. Okay. So here's what we've got. First, let's kind of look at this one at a time. The scales on our histograms are looking a little funky right now. So first, let's just look at, I'm going to filter out. So we're only looking at secondary centered. We'll say operation equals secondary centered, or operation equals secondary school. So we can do a filter within our ggplot call, and then we can look at these two distributions. Now, what do we note here? The initial distribution for secondary school goes from 0 or 3 to 75, as we observed in the initial data, or 76, right? So that's the initial distribution. When we center it by differencing the means, that is the plot on the left, we get the exact same distribution. The bins are a little different, but it's the exact same distribution. Maybe we'll do it with a density so it'll show it a little more cleanly. Of course, the shapes are not looking exactly the same, but I promise the distributions are exactly the same. Maybe if we do it with like bins equals 150, so each data point gets a cell, right? So here you can see that the actual distribution of the data looks exactly the same. We don't need 150, let's do it with say 50. But all we've done is we've picked up this data that used to be centered at like 25, and we've made 25 equal to 0. We've just subtracted it. And so when we subtract it, what we do in effect is we move it leftward. So this is our initial variable on the right, and we've picked up the whole distribution and we've moved it to the left a mean number of units, right? So the mean of IPV $ secondary school after we remove missings is 24.4. So effectively, we've taken every single data point on this left-hand plot, subtracted 24.4, and obtained this new distribution. The shape of the distribution is identical, but the location of it has changed by 24. Hope that makes sense. So when we recenter a variable, what we do is we basically pick it up and we shift it to the left or right, depending on what our centering measure is. In this case, we're using the mean of 24. So now you can note that the mean of our centered variable is by definition 0, right? So if we take the mean of IPV scale $ secondary centered, we'll see that it comes out to be 0. I gotta remove missings again. Whatever, it's 0. Sorry, but it is 0, I assure you. Okay, so that's a center, is we pick up and we move a distribution. Seeing a chat. Yes, you'll see it when we get to clustering. Centering the distribution can be useful if we have variables on very different scales. If we have one variable whose mean is 10,000 and one variable whose mean is 10, we may not want to estimate a linear relationship between those two variables because the scales are really different, and any relationship will have a very, very low correlation coefficient by definition. Centering fixes one part of that problem, but it doesn't fix the whole problem. But there's a lot of reasons why we may want to define the intercept for a line to be 0. Right? Effectively, what we're doing here is we're setting our y-intercept in any linear relationship we estimate from here on out to be exactly equal to 0. And there's a lot of mathematical cases where that's very convenient, right? When we don't have to have a separate intercept, we can just work exclusively with a slope measure, right? Effectively, we're zeroing out an intercept term in any linear relationship we're going to estimate between this variable and anything else. That sounds a bit technical and wonky right now, and it is, but the benefits will become clear as we keep going. Now, I just want to kind of show you what the operations do and to define what these operations are before we start to use them in too much detail. So we looked at centered. Now let's look at reshape. Okay, so the reshaped measure takes the takes xi and divides it by the standard deviation, right? So what we do here is we take the secondary school measure, (25.2), and we divide it by the standard deviation of the distribution of the secondary schooling variable in the observed data, which in this case is the SD of IPV $ secondary school, right after we remove missings, is 15.8. So to get 1.59, we divide 25.2 by 15.8 to get a rescaled version of the variable. Now what we have is a variable whose mean will be equal to the ratio of the mean to the standard deviation. So it'll be equal to like 24.4 divided by 15.8, 1.5. And we can see that the mean of this distribution is about 1.5, right? And it will have a much more compressed spread, right? Because we went from a range now of 3 to 75 to a range on our new variable. Or we could just do this with summary. We'll do it with summary. Less work. Oh, right. I have to filter for operation equals secondary shaped. Our new range is 0.2 to 4.7. So we've dramatically compressed the size of the distribution, the range of the distribution, right? We've reshaped this to this. So we have a much higher peak, right? And much less spread. But however, right, so this is on the original scale. We've constrained our x-axes to be identical across these two plots. What'll happen if I allow the scales to be free and I allow each to have the same, have their own x and y axis? If I do that, the distributions again look identical, right? So if we look at it now on a 0 to 4 and compare that to the distribution of the original variable on a 0 to 75, we can see that this distributions actually look identical, right? All we've done is put it onto a new scale. We put it onto a new unit of measurement, that is the standard deviation unit of measurement. So the distribution of the data is functionally the same, which implies that the linear relationships we may, or correlations we may estimate between a reshaped variable and another variable will be identical to those that we would estimate between the original measures, right? They'll have the same underlying linear relationship. It's just going to be on a different scale, and that can be really handy. So then let's compare reshaped to centered. Let's compare, I'm sorry, to scale. So we have the full scale operation does two things. It centers and reshapes. All right, so let's look at what that does. Now, and let's remove our free scales here. Now, what do we see? We see that the shape of the two distributions, again, is identical, but the location is different. So for the reshape, remember, we're centered at about 1.5. That's the ratio of the mean to the standard deviation. On the scaled variable, we're centered at 0, right? But the shape of the distribution in terms of the shape of the curve is identical. Okay, so if we preserve the shape of the curve, we can move it around wherever we want, but that can be really helpful when we have things on very different scales. And it's absolutely critical for using some of the algorithms that we may want to use to detect structures in our data, right? But doing these kinds of transformations, while it reshapes the data, it actually preserves information, right? We don't lose information when we center things. We don't lose information when we rescale them, as long as I store that original value somewhere. As long as I store that mean and that standard deviation somewhere, I can always undo the transformation, right? So I haven't lost anything when I do this. So all that said, let's move on. So we've kind of reviewed z-scores, right? A scale and an original variable will have a slope of 1 when we plot them against each other. They have a correlation of 1. When we know secondary school is equal to 40, we know with certainty that secondary scale is equal to 1. They're perfectly correlated with each other. Okay, so let's move on to clustering now that we've reviewed z-scores in some detail. So data are often clustered based on unobserved or unobservable characteristics. Sometimes they're observed, sometimes they're unobserved. We call these latent structures, right? So when we look at our data, there may be underlying patterns or groupings in the data that we may not have variables to identify, right? Maybe we do, maybe we don't. We can call that a latent structure, right? Something that's present in the data that we're not directly observing. K-means is an algorithm that we can use that identifies K, where K is an integer, right? So 1, 2, 3, 4. We can use to identify K latent groupings in our data based on proximity of observations for specified variables, right? So what we can do is we can take our data and we can say, data, I think there are 4 groups in the distribution of these measures. Find them for me. And the K-means algorithm will do just that. So here's the algorithm, right? An algorithm is quite simply a list of instructions, right? A concrete list of instructions that we give to a computer to execute some task, right? So it's a sequential set of steps used to solve a problem. So the other definition I want to give you before we get going is a centroid. A centroid is the mean value of a cluster within a group, right? So we have various, effectively a centroid is just a kind of location of our estimated center of mass for some group that we've defined. And those are going to move around, right? So they're just little centers. So we're going to choose randomly the initial centroids for each of the K clusters of interest. So if we say there are 4 possible groupings in our data, we're going to randomly select 4 possible centers for those groupings. We're going to assign each observation in the data to a cluster, 1, 2, 3, 4, with the nearest centroid. Then we're going to assign a new centroid based on the distribution of those that we assigned to the group. So we're going to move the center based on the empirical distribution that we assigned to the group. Then we're going to repeat steps 2 and 3 until we don't get any motion in that center. So let's actually look at this, right? So the number of clusters we choose is arbitrary. We can name however many clusters we like. Often this will be informed by some insight we have into the data. How many groups do we think there are? And R will then randomly select starting values for step 1, right? Step 1 is random, but it's going to then learn from the data, right? This is a very crude technique of machine learning, right? Effectively, we're going to give R 1 input, well, 2 inputs. We're going to give it our data, and then we're going to give it the number of clusters we believe exist in the data. And then from that, R is going to tell us what the groupings in the data are, which variables belong to which group. So let's start in the top left here. We're going to say there are 2 clusters. So our K here is exactly equal to 2. I don't know why I'm saying exactly equal. Our K is equal to 2. So we have a blue and a red centroid, right? The blue centroid is up here. The red centroid is down here. We're going to divide them into groups based on which centroid they're closest to. So we're going to divide the data into 2 groups. All the blue dots are closer to the blue X than they are to the red X, right? And so we divide the data based on proximity to those 2 centroids. And then what we do is we take the average values for X and Y for these observed blue dots and these observed red dots. And so those X's move, right? The center of the distribution of the blue dots is now here. The center of the distribution of the red dots is now here. Once we've done that, we split the data again. Now we're going to say which dots are closest to red, which dots are closest to blue, and we're going to end up with a reclassification, right? Obviously, these blue dots up here are now much closer to red than they are to blue. So these blue dots that were up here now become red dots. They are assigned to the red group. Whereas these red dots that were in the bottom left quadrant over here are assigned to blue, right? So we have a reassignment based on how the centers, the centroids moved. Now we recompute the center again, right? It moves a little bit because the mass here, the mass of our blue dots has moved down into the left a bit. So we can see that our blue X moves down into the left a bit. Our red X doesn't move very much. The center of mass, though, is up into the right just a little bit. So it moves up into the right just a little bit. And we reclassify again. We don't see much change this time, right? We see a few dots at this edge get reclassified, but not very many. And you can see now that the X's don't move much at all, right? The center of mass hasn't changed much based on that classification. We're going to draw another line, see if we get any reclassification. In this case, we don't. And if no dots are reclassified after that step, then the algorithm is completed. And we've identified two groups in the data. So we started with this cluster of points that had no classification assigned to it. And we said, hey, R, I believe there are two groups in this data. Use the k-means algorithm to identify which observations belong to groups, which observations group together. And in this case, this is what the algorithm established. It established that there are two latent groupings in the data. If we say there are two latent groupings in the data, these are the two that R will detect, right? Now, we're going to get a little bit of variation each time we run this because those starting points will differ, right? We'll have some random error in this process because we start in random locations, right? The blue and the red X start in a random place every time we start this algorithm over. We can fix it if we'd like. We can tell it where to start if we like. But in theory, they should be random, right? If we're going into this with no information about which groupings these are. So that's the k-means algorithm in a nutshell, right? We kind of choose initial centroids. We assign each observation to the cluster, right? So we choose our initial centroids here. We assign based on proximity to those centroids. We recompute in step 3 the new centroid based on the within cluster mean, that is the mean of the blue and the mean of the red, and then we move the centroids to those new locations, and then we recompute based on proximity, that is we go back to step 2, and then we do step 3 again, and then we do step 2 again, and then we do step 3 again, and then we do step 2 again, and if nothing changes in that reassignment, then we end, right? That's when we end the operation. So we can use the k-means algorithm in R with the k-means function, right? So we can say, take this IPV scale variable, and let's say there are three latent groups in it, and I want you to start at 10. So what the k-means algorithm is going to do is it's going to run through the data. It's going to run through that k-means algorithm. It's not really going to show us what it's doing, but it's doing that. It's going to tell us what the averages are for the variables that we've selected. In this case, I've given it the data frame IPV scale, and I've included secondary school and no media. So I want it to identify clusters on those two variables. It's going to tell us what the average is, the average centroids, what the resulting centers of mass are for the three groups. It's going to tell us which cluster each observation belongs to, 3, 2, or 1. And then it's going to tell us the sum of squares by cluster, which is a measure of variation. And then it's going to tell us some other stuff, right? Which is just different elements that exist within this object. If we want to push it further, we don't need to worry about that. But let's look at what we need from this. So this is technically a list object. A list is a special kind of object in R. A data frame is technically a list, but a list can contain lots of different elements of any type, right? So a list is a big object, and we can put whatever we want to in a list. And so in this case, I want to pull out a couple of elements so that I can plot them. I'm not actually going to ask you to use the k-means algorithm in any homeworks, but it's a really cool technique, and it will come in handy when you're doing large-scale data analysis. So I kind of want to introduce it as a way to think about using z-scores and a way to think about clustering that will be handy in the future for you. In order to pull out these objects, I'm going to take my IPV measure, and then I'm going to assign to it the cluster value. So we have this vector here, 3, 2, 1, 3, 2, 1, right, within the IPV k-means object, and it's called cluster. That's the name of the object. So I'm going to pull out that object, and I'm going to turn it into a factor variable on my initial IPV data frame, right? I'm going to remove missings, and I'm going to assign this factor 1, 2, 3 onto my observed data. And then I'm going to also extract the centers from the initial object as its own data frame, right? So we can see where these centers are. So then we can actually use this to plot out what the algorithm has told us about the groupings within the data. So if we give R nothing else but the two variables and the idea that we want to have, we believe there are 3 groups in the data. These are the groups that are identified. R identified group 1 as being centered here, right? We've scaled these variables, right? So now these have a mean 0 and a standard deviation of 1, right? And so the range for secondary schooling now is like -1.5 to 3.5. The range for no media is also about -1.5 to about 3. So the first latent grouping in the data is these countries that have low levels of secondary schooling and relatively high levels of no media. The second grouping is those countries in the middle, right, that have levels of secondary schooling that are near the mean, near 0, and tend to be slightly below the mean in terms of no media. And then we have cluster 2 over here. The order is kind of irrelevant, right? It's just going to find these clusters. We're calling them 1, 2, 3, but there's no inherent sequence to it. Cluster 2 then is over here, and that's the countries that are low on no media and high on secondary school, right? So we've identified these latent groupings in the data. We've identified 3 groups to the data. Now, there's no reason I can't ask R to identify 4, right? If I think there are 4 groups, sure, R can do that, right? Here I asked it to do 3. Now I'm going to ask it to do 4, and it's going to subdivide this high group into 2, preserve this group on the bottom right, preserve this group in the middle, and it's going to say, actually, this group cluster 1, there's maybe 2 groups in there, right? We can say this is one and this is another. But the problem with an algorithm like this is the computer's going to do exactly what you tell it to do, right? So if we ask R to identify 10 groups in the data, it'll do it and it'll report it out. And your question as an analyst is whether that's appropriate, right? So here we've subdivided the data into a relatively extreme operation where we have 10 groups, right? Now note that like group, I don't know, number 9 down here has 1, 2, 3, 4, 5 observations in it, whereas group 10 here in the middle has, I don't know, 15 or 20, right? So we can end up with different numbers of observations in the different groups. It's all just about proximity to those centers, right? Now 10 is probably overkill, right? And so when we use k-means, measurement and design are really important. right? We want to, oh, right, sorry, this is a summary for the whole lecture last week. So we're just going to, when we use k-means algorithms, when we use any algorithm in our data, and this includes like algorithms people are using to predict reoffending in the context of criminal justice. This includes algorithms that Netflix uses to decide what you're going to watch next. The input we give it and the quality of the data we give it are instrumental in determining the output we're going to get, right? So always think really carefully about what you're feeding your algorithm and what you want out from it. We're going to take 5 here, and then when we come back, we're going to pivot to some different topics. We're going to do some advanced coding today, looking at joins of data frames. So I'm going to pause the recording here for a moment, and we'll come back in about 5 minutes. Okay. I would ask if anyone needed more time, but if you need more time, you're probably not in front of your computer and can't tell me via chat that you do. Getting, it's definitely like going back to last year teaching this way, but that's okay. So joining data. A join is a really, really powerful thing we can do with our data to link data frames together, right? So if we have data frames that we want to use multiple variables from across different data frames in the same analysis, a join is a great way to do that. And it's a really important technique for the kind of broader set of tools that I'll call data wrangling, right? Data wrangling is the process by which we can reshape, transform, and otherwise get the data from whatever format we have it in to whatever format we want it to be in, right? So a join is a really critical piece of this. So let's look at some data that we'll use. And again, I just pushed up a new version of the Markdown and PDF for the slides today up to GitHub. If you'd like to re-download it and follow along. You could just paste, if you have notes on the original Markdown you were working on, you could paste that first block onto the new Markdown file if you want to do that. Or just save them as different, that's fine too. Okay, so we're going to work with some political polling data. And it's political polling data of the 2016 presidential election. So you can kind of ignore this comment, but this is the basic structure of the data. We have a ID number that is this is actually a synthetic, this is a collection of polls, right? So it's not a single poll, but rather it's an aggregation of lots of different opinion polls from lots of different states, right? So we have here is the ID, and that's the ID of the opinion poll. That tells us what state the poll was conducted in the state column. It tells us the percent of respondents in that poll who said they support Clinton, the percent of respondents in that poll who say they support Trump, how many days away we were from the election, how many electoral votes that state has, and what the population of the survey was. Remember, the population is the group to whom we want to use our sample to make an inference, right? So in this case, we have different populations we could be drawing from. This population is likely voters. That is those people who are very likely to vote in the election. But there could be other populations of registered voters. That is people who are registered to vote and may or may not choose to vote. And then we could also have eligible voters as another population. That is people who are eligible to register, who are eligible to vote, but who may or may not be registered and who may or may not be likely to vote, right? So in this case, we're restricting our analysis to only those people who are likely to vote in the election. And that's what our filter operation is going to do here. We're going to remove the eligible and the registered populations and only look at likely voters. And we're going to select the 4 columns that we're going to use for our analysis: state, Clinton, Trump, and electoral votes, right? Population is redundant now because we've filtered out all other values, so it's a constant in the remaining data. Days to election, we're not going to work with. That could be interesting, but we're not going to work with it here. And the ID number is just an identifier. It doesn't actually tell us anything, right? It's just a row number effectively. Okay, so here's the results data frame that we're also going to look at. So we want to look at the polls and we want to look at the results. So this is a data frame that contains information on presidential election results by county from 1976 to the most current election. This one runs through 2016. So it doesn't have the 2020 election in it. But what we can see here is that we have a year of the election, we have the state, we have the postal abbreviation for the state, we have the state FIPS, I'm sorry, these are state level results, not county level results. A FIPS code for a state. A FIPS code is a Federal Information Processing System code, and it's an integer that identifies uniquely a state in data analysis. You're going to see these FIPS codes a lot if you do geographic analysis, and they are an alternative to using the postal abbreviation or the name of the state, right? So it's a number where Alabama is 1 and Alaska is 2. Right, and like Wyoming is 53, I think. We have the office for the election. That is what election are we talking about? We're talking about not the governor's election, we're talking about the presidential election. We have each candidate. We have what party that candidate was, whether they were a write-in candidate. And we have the total number of votes that candidate received, as well as the total votes in the state. This version is just the data version we're looking at because old data can sometimes be updated. So maybe we would just want to ensure that we're working with the same version. And then we have a random miscellaneous notes column. So in this case, we can see that, for example, Jimmy Carter in Alabama in 1976 received 660,000 of the total 1.2 million votes for president, right? Whereas Gerald Ford received 504,000 of the 118,000, 1.18 million votes. Okay, so in order to, what we want to do effectively is we want to take data from these polls and think about how accurate the polls were relative to the outcomes in the 2016 election. So we want to think about how wrong were the polls relative to the truth. In order to do that, we need to take our polling data by state and join it onto the actual election results. Right? We need two pieces of information to assess how accurate the polls were. We need what did the polls predict, and then what actually happened. And once we have those two things together, we can ask the question of how accurate were the polls? How wrong were they? In this case, they were very wrong. We can join two data frames together if we have any common variables in those two data frames. So a join takes two data frames and links them together. It returns it takes two data frames, returns a single data frame where it attaches the values from both data frames based on some common variable. Joining variables should have identical column names, identical column types, and shared values. So how are both of these data sets structured? Right, the polls data is a state level data set where we actually have multiple observations for each state sometimes, but because we could have multiple polls, for example, within Texas or Wisconsin, and we have it structured by the state and then by the candidate. But the results table is structured a little differently, right? On the top, on the polls data, they actually have it in a wide structure where we have 4 columns, and each candidate has their own column. But on the results data, the candidate name is a variable itself, and the percent vote is its own column. So note in the polls data frame, we have 4 columns. In the results data frame, we have 3. I would call the polls data frame a wide format and the results data frame a long format. That is, they contain similar information. They contain a similar structure of information. That is, they contain information on the state and the candidate, but they lay the data out in different ways, right? So in order to make these two tables talk to each other, we're going to need to restructure one of them so it matches the structure of the other. So when we look at these, though, and we think about a join, we can see that the state abbreviation is identical across both, right? So on polls, we have state abbreviation as our 2-letter state postal code. On results, we have the same information contained in a variable named state PO. So in order to meet the conditions of having identical column names, types, and values, what we're going to want to do is rename one of these variables to join them. So state abbreviation is common. Candidate is a column in results. It is spread over column names in polls, right? So here, candidate in polls is a column name. Clinton has one column, Trump has another column. But here, candidate is its own column where Clinton and Trump are in the same column, right? And then the numeric value is represented in a third column here, percent vote. We want to join such that the election results for each candidate are joined onto each poll for a state. So we want to put effectively, we want to match, what I'm saying we want to do is we want to match results. We want to transform polls to look like results. And we want another column here. We have percent vote here, but what we want to add to this is poll result. Or rather, sorry, we want to, the election results are joined onto each poll. Okay, so we actually want to preserve the structure of polls. And then we want to join the election results onto it. So then we can compute errors. Okay, so let's, we want to look at Nevada poll results for Clinton, and those should match onto Nevada election results. So we have perhaps more than one poll in Nevada, but onto each of those Nevada polls, we want to attach the actual results from the election. So the first thing we need to do is we need to do the rename, right? So we're going to rename state PO into, we're going to take our polls variable, and we're going to take the state variable and rename it state PO, right? So now we have 4 variables in our polls table: state PO, Clinton, Trump, and electoral votes. So a note on the tidy data structure, which is the data structure that ggplot really strongly prefers, and the tidyverse packages generally work best under, is that each column should be a variable, and values should not be stored in column names. So for example, here we have a variable stored in the name of the columns. That variable is the candidate, right? We have a column for Clinton and a column for Trump, but they actually contain the same variable. That is the proportion of the vote share they got, right? The percentage of the vote they got. And we've used the name of the candidate to create a name for a column. But in doing that, we've actually taken information out of the data frame and put it in the name of the columns themselves. So tidy data is typically in a long format where we do not store values in column names. Instead, we want to store each variable in a column, right? So we want to collapse the Clinton and Trump columns into a single numeric column and then a single character column that names the candidate. So what we're going to do is we're going to take the candidate name from the column and we're going to add a new column for candidate. This structure will match the structure of the results data frame. And to do this, we can use a function called pivot longer that I showed you a little bit earlier today. We can take our polls object and we're going to pivot the table to be longer. That is, we're going to take it, it was a 4 by however long the data frame was, and we're going to effectively double the length of the data frame. We're going to pivot it from wider to longer. The columns we're going to transform are the columns Clinton and Trump. And this colon notation says all columns between Clinton and Trump, right? And if we go back to look at the data, we can see that all columns between Clinton and Trump are just Clinton and Trump. We're going to put the names into the candidate field. So that is, the names of those columns are going to go into a new column called candidate. And the values from those columns are going to go into a new column called poll result. So we're going to get a new data frame that includes the state, the electoral votes, and now candidate is in a column and poll result is in a column. So we're going to end up with a data frame in polls long that has twice as many rows as the initial data frame. This is a reshape of the data frame where we are moving from a wide data format to a long data format. Okay, so now that we have this in a long data format, do we see any other problems prior to joining? Let's look at the data for a second. We want to join now by two variables, right? We want to join by state, but we also want to join by candidate because what we're interested in doing is subtracting the poll result from the percent vote. We're interested in obtaining an error, a prediction error, right? We want to think about how wrong the polls were. In order to do that, we need to link the data not just by state, but by candidate. And what do we see as a potential problem here? State PO matches, right? We see that we have two-letter postal codes across state PO. So that's fine. But what we have some differences on are candidate. Here, the candidate is simply the last name. Here, the candidate is the full name. Those will not match as it currently stands, right? Clinton as a string is not equal to Clinton, comma, Hillary, right? So we need to modify this in order for it to match appropriately in our join. The way we can do that is with a simple case when, right? We can take a mutate of our candidate variable, case it when, and we're gonna simplify it to just last names, right? We don't need the first names are kind of superfluous at this point because we can distinguish the two candidates based on their last names. So we'll recode those cases in results where candidate is equal to Clinton, comma, Hillary. We will call those Clinton, and candidate equals Trump, comma, Donald J will be recoded to Trump. And we've seen this before, right? This is the simple case when operation where we're recoding variables. Once we've done that, we can, another way we can do it, sorry, this is a sort of, the way we can do it with a conditional statement on a case when is with, this kind of direct recoding. The other way we could do it is with the word function, which comes as a string manipulation. If you want to do this, you could extract the first word from candidate, but then we would also need to remove the comma, and that gets a little trickier. So we could do a string replace function. We could use the string replace function from the string R package, which is loaded in with tidyverse. And after we've taken the first word from the vector candidate, which remember the vector had Clinton, Hillary, Trump, Donald J. What the word function does is it looks for spaces and it removes the first continuous set of characters that occurs before a space. So if we say word comma one, it says, give me the first word in that string. In that case, it'll give me Clinton, comma, Trump, comma, Clinton, comma, Trump, comma. And then I want to do a string replace where I take the comma character and replace it with nothing. So I'm going to take from the candidate vector, find all commas, and replace them with an empty character that is nothing, not even a space, just delete the comma. That's what that code does, is it looks for commas in the candidate vector and deletes them. So now we get a clean name. Either of these solutions work. I just wanted to show you kind of multiple ways that we could think about solving the same problem. Perhaps we have a candidate list that's much longer. Perhaps we have 30 candidates. And rather than going through conditionals for all of them like this, these two mutates. First, take the first word, which we know will be the last name, and then remove commas. If we have a large number of candidates, this will be much more efficient than writing out conditions for every single candidate. Right. And we can also provide we can nest these, we could do the string replace after we do word. So this is effectively the same thing as I just showed you, but we're going to run the word function. And then after we are going to take the output, the vector that comes out of the word function, and then we're going to run our comma deletion over that to get the same results. Anyway, that's kind of an advanced way to do the same thing using string manipulation functions, which we'll see more later too. Strings, again, are characters, right? They're collections of characters. In computer science, they're typically called strings. And there's a whole suite of functions that we can use to interact with strings, right? Lots of complexities. Obviously, when we're talking about written words, there's lots of different things that can be going on there. There's grammar, there's punctuation, there's all kinds of things that we could think about manipulating. Okay, so let's go back to joins. Left join. Now, so kind of we've reshaped our data to where we have a harmonized format. Polls and results are in the same format. Now we want to stick them together. And typically what I'm going to recommend you do when you're doing a join is to use a left join. What a left join does is it takes one object on the left-hand side of your command and it preserves that object. To that object, it joins the object that you give it on the right-hand side. So it takes the object on the left, looks for matches on our key columns to the data on the right, and then pulls the data in from the right that matches and glues it onto the object in the left. And it preserves the structure of the object on the left. Retains all of the rows in the left-hand object. It potentially removes rows in the right-hand object if there are no matches. So if we have rows in the right-hand object that we do not have matching keys in the left-hand data frame, they will get removed in the join. All columns are preserved. So for example, we could take our polls long data frame, that is after we've cleaned it and reshaped it, and we could join it to our results data frame, again, that we've cleaned. Cleaning is a kind of general term for these kinds of data manipulation procedures that we do to reshape and restructure our data into a format that we can use it. We call it data wrangling, data cleaning. So we joined it by, so we took polls long and we said, again, that we were going to use the state PO column and the candidate column as our joins. And so what we've done with that is we've taken our poll results now and we've attached the percent vote from the results table onto this, right? The results object had 3 columns, right? State, PO, candidate, and percent vote. So 3 columns. 2 of those columns were matches to columns that occurred in the polls data frame. So in our resulting object, the only thing we're actually adding in from results is the percent vote column. We just want to attach percent vote onto polls. And we can see that we've done that here. We have our poll result, our 4 columns for our polls data frame, and now we've added a 5th with percent vote. And that's going to be exactly matched onto candidate and state PO. Right, so we've taken 2 data frames now and merged them. The book shows you the merge function, which does something similar, but the syntax in the join functions allows for a lot more flexibility and precision on how we manage the join. So I strongly prefer the join functions to the merge function. Merge as a function can join 2 data frames. It's just a lot more finicky to work with. Now, what we do want to check after we do our joins, because if we have redundant values on some things, we may end up with different dimensions in our resulting object if we have multiple matches. So in this case, we want to use the dem function to look to confirm that all we've done is add a column, right? So dem, which tells us the number of rows and number of columns for dimensions. We can see that the dimensions of the polls long object, our initial object, is 1,454 rows and 4 columns. And then our joined object, polls and results, is 1,454 and 5 columns, right? So all we've done is add a single column and it's matched exactly onto the values, right? It's not like we've taken the column from this other one and just stuck it onto the side. We first matched it based on state and candidate. Huh, okay. I thought we had more today. Oh, okay, so that's a join. And apologies. So I kind of broke up the lectures. We have substantive content on prediction that we're going to do next time. So effectively, once we have these data frames joined, we're ready to do a lot of analytic work to think about the accuracy of these predictions. So we're going to call it quits there for today. A little short. Doing these Zoom lectures, I feel like doesn't we don't get as much dynamic kind of interaction as we do face to face. But again, your only homework is to complete the homework we assigned last week. The Slack channel is open, so throw any and all questions about that homework into it. As a couple students have already noted, it is a little bit tricky in the interpretation. So read it carefully and think hard about what you're seeing from the results, right? It's going to take some, the results are not going to be immediately obvious in terms of what they mean. So you're going to need to kind of think about the research design, think about what the question is trying to ask, the study is trying to ask, and think about what the results show you. Again, throw any questions at me. We're going to pass on office hours today. I've got to do childcare, but if you want to set up a Zoom meeting over the next few days to talk about the homework or anything else in lieu of office hours today, please just drop me a line and we'll schedule that. Any thoughts or questions before we close? Okay, well, be safe, stay well.